Hey guys, so welcome back to your next class of Catalyst Concepts. Today we are going to be looking at a new topic. It is called as electric circuits. Now, this is a word that you are familiar with. Circuits is something you must have heard in general, like lots of people say, right? So it is a very simple thing. We have actually looked at electric circuits throughout this chapter. We spoke of them, we just never explicitly defined it. Okay, so if I have to define an electric circuit, I'll call it as a closed path of wires and battery. A very simple way to put it. By wires, I mean any sort of conductor, which is generally wire, and by battery, I mean either a battery or any sort of power source, even the wall outlets that we have. Okay, so if you create a closed path with them, then this is called an electric circuit. Okay, and only when the path is closed will the electricity move through. If it is not closed, say for example if there's a gap, then the electricity will not pass and your circuit will not work, right? So a very simple example of this would be like this. If I have a battery connected to wires like this, now, technically, this is an open circuit because the wires are not touching. This is a full open gap. In a circuit, we have few other components also. There are few parts. One of them being like loads. Okay, like anything that uses the electricity to run, like your bulbs, your fans, your fridge. All of these are essentially loads, what we call them. Okay, we can also call them as component. Okay, so a symbol for a component is we generally so far we've drawn the bulbs, right? It since it's not just a bulb, it can be anything. We have like a generic symbol, just like for battery, we have a normal symbol. We have one for load, and we put it basically a zigzag lines like this. Okay, just put like four peaks like this. That becomes your load. Apart from this, most circuits also have something called a switch, right? Something like this. We draw a switch like this. What a switch does is it will open and close the circuit. So every time you switch is on, that means the circuit gets completely closed. It becomes a closed path. This is basically when the switch has broken the circuit and current won't flow. Basically, when the switch is off. If you turn it on, it will kind of join these wires back together and it will become closed path. Okay, this is just a symbol. This is not actually a break, but if you see, the battery is a closed object, right? So don't say that there's a gap here and the circuit. So that's not true. This is just a symbol. This is one thing. Okay. Now, there are majorly two types of electric circuits. Okay. By that I mean to say, if I have to connect multiple things in one circuit, because we know that in one electrical circuit we generally have more than one thing, right? For example, in your house you'll have bulbs, you'll have fans, you'll have lights. A lot of things are connected to a same circuit. So if you have to do that, then what we'll do is we can connect it in different ways. One of the ways that we connect them is what we'll talk about for today, which we call as series connections. Okay, series connection. Okay. Now the word series generally means anything that comes one after the other. Okay, and even over here it kind of means the same thing. Okay, so if you ever connect things one after the other, you say that you have made a series connection. Okay, so a series connection would look something like this. You have a battery. Okay, for this one I will eliminate the switch part because it's not really essential right now. So I'm going to assume that I have three loads. Okay, say I'll call them the first load, then second load, third load, like this. Okay, this is my battery, my conductors, and my three loads. this would be a series connection. There's just one single path for the current to flow. So current would flow like this, through this, and then over all of these, and then back here. Just a single closed loop. If you see, the current is always constant. How much our current is going out, or moving from here, is going to be the same current at any point in your entire circuit. Okay, so we say in a series connection, we'll say that the current is constant. Okay. However, what is not constant is the voltage. Okay, the voltage is not constant, but the current is. Now, think of it simply like this. There's just one single road for the current to go. If there are 2 or 3 different roads, some current will go this way, some current will go that way, some current will go that way. So that is why, since that is not there, we say current will be constant over here. Okay. Now, when we have a diagram like this, I can say that since there are 3 different components, each of them will have a different voltage over there. Okay. So say that the first component has a voltage V1, second one has a voltage V2, third one has a voltage V3. That is basically done. You spoke of voltmeter, right? If I use a voltmeter and measure the connection from voltage from here to here, from this point to this point, I'll get some voltage V1. From this point to this point, I'll get some V2. From here to here, I will get V3. Okay. But instead of that, if I measure the voltage from top to bottom, if I measure the voltage from top to bottom, basically, if I measure the voltage across all of the loads at once, okay, basically from one end all the way to the other. If I measure the voltage all across, I'll notice one thing. That is, if I take this voltage, it will be nothing but the sum of my independent voltages. Okay, the total voltage across all components is nothing but the sum of the individual voltage of each component. Okay, this is one thing to keep in mind. Now, each voltage or each appliance, more correctly, has its own resistance. Okay, like a bulb will have one type of resistance, fan will have another, toasters will have another, fridges have another, like that. So since they each have their own resistance, we'll also give resistance values to them. Okay, so I can say that for the first appliance, it has a resistance of R1, the second one an R2, and third one is an R3, for example. Okay. So if I had to redraw this diagram, I would say something like, okay, I have an R1, R2, R3, and overall voltage across all these resistances is V, and the current flowing is I. Now, what is this total voltage? Oh, sorry, total resistance. Okay, if I have to replace all of these resistances with just one resistance, and it has to be of the same amount. We know resistance is in ohms, right? Okay, so if I have to replace this resistance with something in such a way that the current and the voltage will be the same, but there's only a single resistance instead of multiple, we call that as equivalent resistance. So I'm trying to look for a connection between this equivalent resistance. How much could this be if I have these 3 resistances with me? Okay, just follow this. It's not very difficult. So I can say that V equals to IR. It's a formula that we have studied already, right? So by that logic, I can say V1 is nothing but IR1. The first voltage with its first resistance and current multiplied. Same for the second and same for the third. Okay. Now we also know that the main voltage is nothing but I into R equivalent. Since if it's a single resistance, I'll call it as equivalent resistance. Now from here we know that V equals to V1 plus V2 plus V3. You just substitute all of the values. I into R equivalent is nothing but IR1 plus IR2 plus IR3. Okay. Here, instead of putting the LHS, I put only RHS in this equation. So if I see I into R equivalent is nothing but I into R1 plus R2 plus R3. I is common in all of these three. So I'll just cancel I and I. The final answer that I get is R equivalent is nothing but R1 plus R2 plus R3. Okay, so the equivalent resistance is nothing but simple sum of all of the resistances combined. Okay. That means to say my resistance is like 2 ohms, 3 ohms and 4 ohms, for example. So my equivalent resistance would be 2 plus 3 plus 4, which is nothing but 1, 2, 3, 4, 5, 6, 7, 8, 9 ohms. Okay, that means if I want to recreate the same circuit with the same amount of resistance current with just one resistance, I can make it like this. Okay. I'll make it single resistance of 9 ohms. Okay, that is what it means. Okay, just remember this is the relation for series resistance, series connection only. Okay. Now, so that's it for today. We learned about what is a series connection, how to draw it, and what is the connection between the voltages of each component and the equivalent resistance if we have to find it. Okay, so that's it for today. I'll stop right here. If you have any questions, doubts, please drop them in the comments below. And I'll see you again in the next class. Thank you so much.